Greetings, engineering fans. This is episode 15 of my engineering Oddcast, and today we'll be taking a look at progress on the C++ project that we kicked off in the episode 13. Hope you enjoy. The remainder of this episode is going to be largely screen capture as I show you the code that I've been working on and the project structure in terms of a Git project and a CMake project that I'm using to explore this space. Here's the code I have in my project after about 6 hours of work. So starting from the outside, we are going to be using CMake. Again, arbitrary choice. I could have chosen any build system. I'm going to start from C++ 23, which is the current standard, because if we're thinking about changing the standard, it can only change into the future. And so we need to start from at least now, if not the near future. I use C-test, which I've not particularly experienced before, but it seems to be working okay. And then everything is in subdirectories. So I've got one called failures, which as you can see is commented out. I'll explain that in a moment. And one called test, which is, again, I'll take you into there in a moment. So let's look into the test directory. So I'm using these tests. These are absolutely not the way you would normally use tests, which is to test that your code does what you think it does and doesn't do what you think it doesn't do. I'm kind of abusing that, the test mechanism for my own purposes here. So if we take a look at this test, this is just checking the static property that if I have an unsigned int, I can convert it to a customer ID. And this will be return a 0, which is a C-test success if that's true, and it will return a 1 if it's false. It doesn't actually do anything at any code at runtime. This is entirely processed at compile time. And then we have this test that if you've got an unsigned int and you want a customer ID, that conversion isn't implicit. So this is actually going to be true if you can implicitly convert it. So we just have that return a failure and it be successful if this is not true. So taken together, these two tests say if I've got an unsigned int, I can get a customer ID by static cast or some other explicit conversion, but I can't use an unsigned int where I would require a customer ID. Then we have that you can get a price from a line price. I'll explain all these types of for in a moment. Explicitly, you can't get it implicitly, and similarly, now we have you can't get if you've got a quantity, you can't convert it to a price at all, whether explicitly or implicitly. So that's the explicit test. This is the implicit test. We were going to need, if we wanted to cover the full grammar that we actually want from our set of types, we would need vastly more tests than this. This is just a start of such a system if you want to view it as that, but I've no intent to finish it. And then this is kind of a real test, which is because I didn't trust myself using deduced this to get the syntax correct. So I wrote this test to verify that my pre and post increment operations did affect exactly the object that they were meant to affect. And so that's what these two tests do. So these are the only two that are actually tests, and the others are kind of the result of the other tests is not if it's a failure, we have something wrong with our code. It's if it's a failure, then our code perhaps is allowing things that we would prefer not to be allowed, but it is part of it's an input into a decision of whether we want to go one way or another that depends on many other things as well as that. So let's look at the code we're testing with these, or evaluating with these tests. That lives in lib. And let's look at the most basic version. So here it is. We've got our type set, which is customer ID, quantity, price, line price, total price in a namespace fill. And this is the basic type alias that just says they're all equivalent to unsigned int. And I wanted to anchor the project on this for a variety of reasons, but this is obviously the most simple thing you can possibly write. Then this is the next set of operations. So instead of making it a straightforward type alias, we're using enum class to make everything an opaque type alias for unsigned int. And then we can define here the operators we want to allow to exist. And we can see how close we get to the behaviors we want using these as our types. And then the next interesting stable point for a type grammar is to use structs or classes, which are equivalent in C++, in case you didn't know. So I'm choosing to use struct merely because it saves me writing the word public. And in this case, I've made a struct for each of these types. And I've explicitly, within the definition of each class, I've said exactly what it can do. So here's the customer ID, what can happen there, and then quantity has these operators available, price has these operators available, line price has these operators available, total price has these operators available, and then I have some externally to the class defined operators. Now it's worth having a discussion about that trade-off, and we'll loop back to that perhaps in a moment. And then finally, for now, I have the same thing done with technique that I think most people call mix-ins, which I originally heard used as a term in the world of Ruby. But here we have, again, it's a struct per type that we're going to define, but we have a customer ID, but its implementation is pretty much entirely from this class that it inherits from it. So we have this type that says I hold a value of unsigned, and then these two usings are required to make the whole system work. And when we look at quantity, we've got a bit more, a few more mix-ins here, so we can increment, decrement that one, we can multiply it by something, and so on. And then price only has value multiply, line price, we've got a couple of implementations of add as well, and total price has got add and is explicitly convertible to price. And again, we'll loop round and talk about how those work in a little bit. So let's talk about, but let me show you how the magic happens to make these tests test all of these different kinds of type. So what I've done is I've got a set in CMake of all my tests. I've got then a test source list, 4 of them, one for each kind of category of types that I'm going to evaluate. So I've got my aliases, my enum classes, my normal classes, and my mix-in classes at this point. If I need to add a fifth one, again, I would be duplicating that and changing it as necessary. This makes the executable for each of those source lists. This makes the include path correct for each of those executables. This is where the true magic is. So for each of these executables we defined here, when it's being built, I define a preprocessor macro called test types, which has what you need to include to get in to pull in the types that we want to test this time. There are other ways to do this. This is the way I personally prefer to do it, and we'll talk a bit about why that might be. Perhaps, I mean, I think I'll wait to see if anyone wants to argue about it first. Anyway, and then this is standard CMake boilerplate for getting all your tests executed. But let me show you what that lets me have by just running all of the tests. Oh no, apparently I won't be running all the tests because I've got build failure. No, I don't. Okay. VS Code's gone weird, which regrettably frequently happens, and I don't know what goes. Anyway, that's what it should look like. So we run all the tests and we get this mixture of failures and passes. And as you can see at the moment, my mix-in classes and my normal classes pass all of the tests, as in they behave with exactly the limits we would want. My enum classes fail exactly one test, which is the price from quantity can't be done explicitly. And as expected, the aliases fail pretty much every test that was trying to limit conversions, because obviously all of those types are really the same. So I want to stress, though, that these are one dimension of how we're going to evaluate things. It's not. This isn't even, I think, for me personally, I don't feel this is the most important dimension of what we're looking for. We're looking for a balance between do we get the behaviors we want? And also, when we make a coding error that results in the project not building, do we get a sensible error message from the compilers we're using? And also, if we have a runtime problem somewhere inside the program and we have to debug it, are we getting a good experience of debugging the issues? And I think if we can get the best, I think we should look at what is the best experience out of all of these techniques for each of those categories. And then if we're making the decision based on what's available now, we should pick which one we like best out of those availabilities. And if we're thinking about what we might want to design into a future change to the language, we should be aiming to build something that gives us the best in all categories at the same time. So that brings me back to, because I've just mentioned it, that brings me back to this failures subdirectory. So let me save that, and then we will run the build, and we know it will fail, or rather we expect it will fail. And so let me show you the code. Let's start from that actually. So the code is testing, or this is a intentional coding error by the rules that we've set. So we have a total price, and we're trying to add on to it a price. Now our grammar doesn't allow that. We can only add on a total price or a line price to a total price, but we can't add on a raw price. We have to multiply it by the quantity to get a line price, and then we can add that to the total price. So this is a logic error that we intended to catch, and I've provoked it here to see what the compiler says when we do something wrong. And so as we can see, we have 3 failures, but we compiled it 4 times, and the reason we only have 3 failures is that the alias version, where we just use using, obviously doesn't have a problem with this. So we know that from this compilation that if we really want to strictly ban this from working, we can't use aliases, and we knew that already. So now let's look at what we get on the other for failures on the other things. So when it's an enum class, we get this message: error C2679 binary plus equals no operator found, which takes a right-hand operand of type price, or there is no acceptable conversion. So I think that's an okay error message. I would be happier if I could provoke it to say what the left-hand type is. So it would be clear you can't add take a total price and add a price to it. But it at least says the problem is that your plus equals can't use a price. And then if we look at my explicitly, fully written out normal classes, we get exactly the same error message with exactly the same caveats. So it's okay. It could be better. And if we can find a way to make it better, that would be nice, but it's acceptable. Now here we see something interesting. When you go to the mixing classes, the error is different. So it's C2676, which immediately tells us the content's going to be slightly different. And we've got plus equals, and then it says total price does not define this operator or a conversion to a type acceptable to the predefined operator. Now, I don't like that message at all, not least because it's untrue. And I can show you that it's untrue because total price does define operator plus equals. It just requires that the right-hand side is a line price, and I can prove that that's true by making that change and hitting build. So we have a problem there at the intersection of using that mix-in technique and using this compiler, that if you make an error, it is a misleading error message to the person trying to fix it. The correct, like the ideal error message would say total price plus equals price is not defined. It is defined if the right-hand side is line price. And then that would give you great, all the information you need as a programmer to sort that out. However, I don't believe we can provoke that particular message from this compiler. Okay, so that's given you an overview of 2/3 of what I'm trying to evaluate. So I'm trying to get a view over, does this technique limit the grammar in the way that I intended, which is what the test folder is for. And I'm trying to get a view of, does this technique create good error messages that are, accurate and useful. That's what I mean by good in this case. Does it create accurate and useful error messages when a programmer makes one of the errors that we're trying to prevent? Because the whole purpose of this is not only to prevent those errors, but that if we were expecting those errors never to happen, we wouldn't bother with any of this at all. So we are expecting these errors to happen. We know that they're going to happen, and we do need to care about when it happens, how are people going to fix it? And that's the part the failures directory is intended to evaluate. Now, we have one more dimension to this, which is one I haven't yet started doing, and that is to write a sort of golden path program. So there'll be I will create a successes directory and write a realistic bunch of functions and algorithms to go over these types, do the golden path things, the things that we expect to work and should work. And then I'm going to experience what debugging that program is like by provoking some errors somewhere. Like, so if it crashes, what does that look like? If I'm stepping through the program, what does that look like? If I'm just trying to inspect the content of the variables at this point, what does that look like? And that is going to be the third dimension that I feel is very important for doing anything like this. And we will be trying to weight those things appropriately. Or I will tell you what I think, at least, about how I would weight those things if I was having to make this decision. I promised to show you what the mix-in classes look like. So let me show you what how those templates work. So they're all forward declared. Value is parameterized only by the underlying type, as we saw, and as soon as you're using this, you get a default constructor, which is just going to default construct the underlying type. You get a explicit conversion constructor from the value type, and you get an explicit conversion operator to the value type. So that's what is allowing our static casts to and from unsigned in to our various other types to work, is these two lines. And we friend all of the other mix-ins because we want them to have access to this private stored value type. Note that the actual class that inherits from this does not have direct access to this value type, and that's intentional on my part. So here's the mix-in for multiply. The template parameters are what the result of the multiplication is and what the type you're multiplying by is. So you can extend multiply more than once with different other types and different result types. You can't, of course, extend it with the same other type and two different results, here are the implementations of operator multiply and operator multiply equals. So this is how one should do it, in my opinion. We're using the actual raw values for multiply equal rather than assuming that it's the same as multiply and then a sign, which is it's a detectable difference, and I may explore that later if there's any interest, but I think this is the correct way to implement multiply equal. And for those of you who aren't familiar with C++ 23 but are familiar with other earlier standards, this construct here is the new deduced this. So that this is roughly equivalent to if you were to write, so omit this parameter entirely, add const here, and then on the first line write auto const ref self equals star this. Except that when we do this, self becomes a reference to whatever the derived type is, and that's super useful because that lets us get at its type alias base t, which is what we're going to use to find this. So it's definitely a technique worth using. It's basically allows us to do what used to be the curiously recurring template pattern, but without passing in the derived class name anywhere into the superclasses. And then anyway, so add is exactly the same as multiply, except that these stars here have become pluses. Increment, you'll note this is where it gets a little bit cool, because this is now what would have been a curiously recurring template pattern class, but it's not even a template class, it's just a regular class, and it becomes the template magic is only limited to this auto section. And so this is using arrow syntax to say I'm going to return whatever self is, and self is a reference to the derived class, which is pretty wild. And then obviously for post increment, we're going to not return a reference. But we'll return the same type, but not as a reference. Decrement is exactly the same as increment, but it's done using minuses instead of pluses. And then finally, the explicitly convertible, which creates an explicit conversion operator as it's asked for. So all of that's pretty, it's nice and fancy C++ code, but let us honestly evaluate it against the reasonable alternative, which is to just write normal classes. So if we look at our mix-ins, we are forced to write this bit of boilerplate, and there's not really a way to avoid that and keep things reasonable. The other problem I see here is, so let's take a look at line price. So this value is an unsigned. That's nicely unambiguous. I mean, it's relatively obvious looking at that what it's meant to do. Explicitly convertible with one parameter is really obvious what that's meant to do. My beef here is with add and multiply, because you're always going to have to say what the multiplier or the add parameter is, and also what the result type is, and they have to be in some order, and it's defensible to make either choice, I feel. So I've chosen to be consistent that the result type is first parameter and the parameter type is the second parameter. If you are familiar with the convention I've used, then sure, you can read this. If you're not familiar with the convention I used, you're looking at this and you don't know what that means, right? Does that mean quantity times a line price is a price, or does that mean quantity times a price is a line price? It could mean either, and you're going to have to go and read some mediumly complex template code to find out exactly what is really happening. So I don't love that. One of the things with using the mix-ins is all of your addition and multiplication operators have to exist on the class type itself, because that's how mix-ins work. You can't acquire free functions in the same way. You can't mix in free functions. That's just how things are. The disadvantage of that is, if we look at in the normal classes, I've preferred to keep the multiply and addition operators separate. And what that means I can do is both these multiplies here are kind of logically the same. They result in a line price. But in the mix-ins case, I have to write on the quantity class that I can multiply it by a price to get a line price, and I have to write on the price class that I can multiply it by a quantity to get a line price. Whereas when I'm allowed to make these operators separate from the classes, I can group, visually here and in the implementation, can group these two functions together, they're both aspects of the same operator, which is irrespective of the parameter order. If you take a quantity price, multiply them together, you get a line price. And similarly here I've got this pair is the same principle. Irrespective of the order, if you have a total price and a line price and you add them, the result is a total price. And in fact, this belongs part of the same set. Like, the fact that this relation of total price is addable with line price to get a total price implies that there should be operator plus equals on total price and line price. So from a like, what is the actual grammar here, and has it been implemented completely and correctly? It's a little bit easier potentially to audit that from these external definitions. Like, if one of these three exists, all of these three should exist to be a consistent mathematics, basically. Whereas, and in this case, it's a little bit easier to see that, arguably, than if I'm looking at mix-ins, where I have to check that is, if that's there on this class, it must also be there on this class. And I feel that if I had to visually audit this for is it complete, it's easier to do that here. I will publish the GitHub repo, and it will have a tag for episode 15. I'll link it in the description so you can follow along if you've been finding my screen difficult to read or my font difficult to read, which I can certainly understand. And one of the reasons that I'm putting it on GitHub is so that I can easily synchronize it to my Linux machines where I'm testing with GCC and with Clang. I want to find a solution here that works for all three of the major compilers that I have worked with in my time in business, which are Clang, GCC, and MSVC. And I feel it's important that I test anything I'm doing across all those three platforms, because I wouldn't be happy if I found a solution that only worked for one of them, or for 2 out of 3 even. There are, of course, other major compilers in the world, but I am less experienced with those and I don't immediately have access to them. So I will roll them in later. If I find something that works for these three, we'll start to try and look at anything else that has a C++23 mode. As we've seen from these tests, I can swap in and out definitions of these types, and I can make a type system that is equivalent in the golden path. So when nothing is wrong in the code, it's equivalent to use the aliases or any of the more restrictive techniques. And what that means potentially is that I could use the aliases for my normal builds, and I could run in my CI process, perhaps I could run another build which uses one of the other definitions that is more restrictive, just to verify that no operations I'm intending to be illegal are happening. Now, the advantage of that is that the alias code I expect to be much easier to debug. I expect to give much better error messages, like without distractions when something that's nothing to do with things we were explicitly trying to ban has happened. So normal development is impeded to a lesser extent than with the other techniques. But because I can have in my build pipeline a gate that says unless it builds with the restrictions turned on, you're not shipping it, I will know that I have not actually done any of the illegal operations or the operations I'm trying to ban. Now, there's obviously dangers with that, because conditional compilation can detect the difference between type aliases and any of these class techniques, and so you would not be. It's not necessarily the case that you would be testing compiling equivalent code. So that's one caveat. And then another caveat to actually doing that is you still have to take on the maintenance burden of all of this class stuff. And it's perhaps too likely that that would rust and stop working as intended, and you would stop, therefore, having this valuable detection of errors in CI working. So those are potential problems with actually doing that. But it's an interesting avenue, and the fact that that is a not totally unreasonable thing to think, makes me wonder if there's a way to say, do you know what, this is what you type, then some kind of magical annotation goes here, and then we statically analyze your code versus this. So with these definitions and this grammar, we run a static analyzer to check that you have not broken the rules that you said you have. It's obvious that that could be done. The question is, how does one define that grammar, and is that static analyzer something that you wish to build into the compiler itself, or is it okay for it to be in another tool like Clang Tidy or so forth? And as I say, this is what I'm thinking about, what I'm going to investigate. So I do not know the answers to those questions yet, but I do intend to explore those in the future. It probably won't be the next thing that I do. Finally, for some more foreshadowing, this kind of construct with certain combinations of parameters and what conversions are available can cause problems because operators not all being within the same overload set. And I will be trying to, it's a problem I have run into with mix-in type classes in the past. I will be trying to recreate that problem now because I am not certain that it's still an issue with C++23. I'm not certain that it's still an issue with this shape of mix-in definitions. And if it is still an issue in C++23 and with this shape of mix-in definitions, I'd like to get a small example nailed down so that I can explain the problem and what you can do about it. That's a wrap for this episode. See you in the next one.